Okay, very good morning to all participants. Um, Hello to everyone in Malaysia, in Indonesia, in Australia, in South Korea, India, Qatar, Pakistan, and other countries that I couldn't mention one by one. Today, Malaysia Process Control Society, my PCS, is happy to organize the first session of our webinar series 2021 on process control. And this morning we are very privileged to have Professor Thomas Marlin from McMaster University, one of the legendary authors of process control textbook. And we would be happy this morning to listen to his presentation entitled Process Control Education in the Era of Industry 4.0. So without further ado, I would like to invite Professor Marlin to start the presentation. Professor Marlin, over to you. Thank you.
Oh, thank you very much, August. And thank you very much to the Malaysian Process Control Society for the invitation, very gracious invitation. And good morning or good afternoon, or for me and maybe a few others, good evening. We're getting used to these video conferences and they offer nice opportunities to see people from all over the world. A couple days ago, I was watching a IFAC conference, and there were speakers from Hong Kong, Germany, and the United States. So these webinars, although we'd like to be meeting in person, they give us great opportunities. Unfortunately, one of the opportunities I'll be missing is I won't be able to visit Malaysia, which I very much would like to do. But my loss is the benefit of the budget of the Process Control Society, no airplane tickets. My topic today is process control education in the era of Industry 4.0. I had not previously considered this very much, so I enjoyed investigating it and putting together my ideas. And I hope that this talk my comments will stimulate you so that encourage you to look deeper into the topic and to add your comments and questions either at the end of the talk or through the talk. Mr. Fauzi will be monitoring the chat, and if some of the questions should be clarified during the talk, he will just bring the questions to my attention immediately. Otherwise, we'll accumulate the questions and comments and deal with them at the end. But please add it in the chat as we go. So before I get into the talk itself, if you want to evaluate the message, you have to know the messenger. So just a little bit about my experiences and my points of view. Before I became a professor, I worked in industry for 15 years, mostly in process control, also building dynamic simulators for operator training. And the last few years in industry, we're working on real-time optimization. In a transition between industry and academia, I spent some time at the Warren Center for Advanced Engineering in Sydney, Australia, and we performed a one-year study on the benefits of process control and published a book. It was published by the Instrument Society of America, and that had 7 industrial case studies and took about a year to complete. Then I went to McMaster University as a professor in chemical engineering. And this is just a little screenshot of the McMaster Advanced Control Consortium. And a number of professors collaborate in this consortium along with about 20 graduate students. And we have joint projects with a number of companies. So it gives the students a great opportunity to have interaction with industrial practitioners and have case studies in their research coming from the companies. So I was the director for the first 19 years. It's been in existence for over 30 years now. The screen capture is a little old. It's probably around 32 years old now. So while I was at Mac, and then since I've retired, I've been maintaining this website, the Process Control Education website, where you can access my book and e-lessons and other learning materials at no charge. Some of the topics I'll be talking about today are actually covered on this website not under process control, but under process operability. So when I talk about some of the issues like flexibility and reliability and troubleshooting, there are chapters, book chapters, and PowerPoint slides, but they're not in the process control section. You have to look over here under process operability. And then what keeps me busy besides maintaining that? Now, recently, I've been working with Academics Without Borders. And what this organization does is that it goes to developing countries and works with young faculty members to help them build their research and teaching capabilities. So that's one of the things I'll be doing next week, working with some groups on their research proposals. So that's me. That's me. That's not the important thing. The important thing is the topic. So we have in the outline, I'm going to first talk about Industry 4.0. It's a very nebulous thing. It's everything to everybody in some sense. So I'm going to try and pick out the key aspects that might be most important for chemical engineering, and then talk just for a moment about whether we're in a revolution or an evolution in the changes to process control. Then I'm going to talk about the education, and I'm going to talk about process systems engineering topics, not just control, but design, optimization, and data sciences, and how we can relate these topics to the Industry 4.0. And then I'll try and summarize the status and some future steps that we could take to improve the situation, because wherever we are, we can always do better. And of course, please continue to add your comments and questions in the chat. Now, we'll look at these topics in a little more detail, but where does Industry 4.0 come from? Well, my best research is that it was introduced at the Hanover Messe. Messe is just a trade fair in Germany in 2011. And it's developed to be a sort of a guide us and set the basis for Germany's plan for developing new technology and businesses. So it didn't come from the academic side, and it didn't come really from the user side. So, and it covers a very, very broad range of topics. There are alternative initiatives like Made in China, Society 5.0, and Smart Manufacturing, and the Industrial Internet of Consortium in the United States. So when we talk about Industry 4.0, that doesn't mean that's the only definition of what's in the future. We have all these others over here, and they're going to have to all at some point combine and collaborate, because we have to have systems that are compatible. We can't have competing software and hardware systems. They won't be interoperable. Okay, so here's one take. This is from the Boston Consulting Group on what Industry 4.0 entails. And it goes, you can see, from advanced robotics to additive manufacturing, 3D printing, and so forth, all the way down to big data and analytics. And not all of these are maybe necessary of interest to the process systems engineering community. Some may not even be in chemical engineering. So I'm going to sort of highlight these items. Simulation, and under simulation, they include optimization. So using simulation for decision making, which can be optimization. the horizontal and vertical integration of analysis of the plant, the industrial Internet of Things, so IIoT, and certainly big data and analytics. So these are the four things that I'm going to concentrate on. Now, things like cybersecurity obviously are very important, but I don't think the chemical engineering community is going to be involved in writing the protocols for that, although we're going to be demanding that the security exists. So let me relate those to a typical chemical process. First, we have the horizontal integration. So that's from raw materials to final customer satisfaction. And the Industry 4.0, they also talk about customer feedback and dedicated customer product design. So you go in and they take your measurements and then they build you a bicycle that fits you exactly. But this is certainly an issue in all of our plants. There's vertical integration from instrumentation and equipment through supply chain, and they're even considering the circular economy where we collect materials and recycle them back. We don't stop at instrumentation here because now the equipment, the pumps and valves and so forth, will be smart. We'll have processors in them as well. And to deal with this range of decision making, we're going to have to use optimization, data sciences, control, and simulation. And some of the key words, the industrial Internet of Things, so a communication among various pieces of equipment without using IP addresses. Cyber physical systems, those are physical systems that have sensing and computation, not necessarily control, but computation at the individual physical elements. And in some cases, autonomous agents, although we probably have had that for 150 years with individual controllers that aren't talking to one another. This is going to be a decentralized system. It's going to have to be interoperable, and that's a key term that industry people use all the time. So in other words, we can mix the equipment and software from various sources into an integrated system without having to write special interfacing for each time we put a new valve or a new pump into a plant. So interoperability from an economic point of view is extremely important. And the system should be modular and scalable, so we can start small and build up as our plant may expand, or as we transfer from older equipment to newer equipment. So this is the picture of the they claim that Industry 4.0, and the Industrial Revolution was basically the steam engine, then was electrification, and then I'm not sure why we choose 1969, but I guess it was robotics, and now we're in the fourth Industrial Revolution. So that's their view of the development of the technology. I have a little different view, so I'm going to share my view with you. But whether it's a revolution or an evolution really doesn't affect anything that we're going to do in the future in this talk. So I think there are three stages. We go back to antiquity and up to the steam engine, let's say. Control systems exist, but they were very few and far between. And it was not recognized that there was a common technology. So as an example, this is a little example of a Greek device by Heron, and it's to pour the perfect glass of wine. So wine is stored in this vessel, and it's poured into this goblet. As this goblet fills, it raises the flow in this other goblet, which then slowly closes the flow to the first goblet. Now that's a feedback system. It was built well before BC became AD, but that technology didn't develop very much, probably because we didn't need it at the time. And so that developed slowly. When we were making pottery, we needed to fire the pottery, and we needed to control the temperature in the kilns. And there were little feedback systems, very, very clever systems, but they were individual artifacts. Once we roughly came up with a steam engine, we started to develop machinery. We needed to have much more advanced controls, but each calculation required a distinct device. So that was an enormous limitation to control. However, it stimulated an enormous amount of control theory. So if we wanted a proportional integral derivative controller, we needed to build an electrical circuit. And if we needed 100 of them, we had to build 100 electrical circuits. So that was until we got to digital computation. Once we started to have programming opened up. Simple PID or MPC, you manipulate 80 or 90 variables. We can do that in the digital machine. So from my point of view, I differ a little bit from the developers in Industry 4.0. I say we're not in a revolution now. Using the terminology from Thomas Kuhn and from the Structure Scientific Revolutions. Thomas Kuhn was the person who coined the term paradigm shift that every manager in the world has overused. And so, but Thomas Kuhn talked about a paradigm shift being when Copernicus recognized that the Earth revolved around the sun rather than the opposite, or when Darwin developed his theory of his understanding of evolution. So we're looking for big changes and not small changes. However, normal science is still important. That does not imply that developments are trivial or of any limited value whatsoever. Okay, so in Industry 4.0, what's the role of chemical engineers? We're not probably going to build it. We're not going to sit down and write the software or design the electronics for the interface cards or whatever. However, we have to be involved along with other user communities in directing the development to high-value applications. In addition, we're going to develop and deploy the decision-making methods, the ones we have now and the ones we're going to need in the future. And we're going to emphasize security and safety. I have never met a computer scientist who understands how important it is to run plants safely and securely. And I've had bad experiences. I can tell you when I was in industry, computer scientists would run experiments in process control systems that were controlling plants. And sometimes we had incidents where we would lose $1 million or $2 million because of software errors that they introduced just to see what would happen. So it's the chemical engineers who own the plant, and we have to absolutely ensure that the security and safety is provided. And I would say this is very similar to the introduction of digital control in the 60s and 70s. So there was a period in which the companies that were building the new digital control systems weren't entirely sure what they were good for, and the operating companies weren't entirely sure what digital control meant. And it took at least a decade to shake that out. And the companies that were the most successful were the control companies, the control suppliers that worked closely with a number of leading operating companies. So that we had directing to development to high value applications, and we were developing novel decision-making methods while they were developing good systems. So chemical engineers are going to play a central role in the overall development, even though we're not building it. Now, process systems engineers are going to be the ones who are going to be doing that for the most part. And so what is process systems engineering? It's fundamental modeling and simulation, process control, optimization, design, data sciences, which is usually not identified explicitly. Just looked at a couple of review papers on process systems engineering published in the last 6 months with maybe 15 authors in the 2 papers, and data sciences was not identified as a central part of process systems engineering, which is not very, I think it is central. And reliability is almost never included in process systems engineering, but it's a key technology and one of the reasons why we need Industry 4.0. So Industry 4.0 goes well beyond the scope of process control. So we're going to need to teach process systems engineering to the people who interact with the I 4.0 folks. And we're going to need the entire array of all of these technologies. So what about the students? This is an opinion. I don't have data on this. A large percentage of the students will need to apply one or more PSE method in their careers. So even if they're working in biochemistry, they can use data science techniques learned in their undergraduate education. Or if they're going into business, they're going to go into supply chain management, they're going to need optimization. Well, only a few percent, I don't know, 5% will actually become process systems engineers and follow that career path. So the principles for Industry 4.0 can be introduced, but not taught in such depth that it requires an additional year or 2 of training. While teaching the undergraduate topics, we can make the students aware of the needs, the kind of things that we need in control and optimization and reliability and so forth. And some solutions that are easy for them to understand, they'll be ready to adapt when they need to see the advanced technologies in the Industry 4.0. And the way to do that is a constant that I'm proposing is a concentration or a stream that will make the PSE available to many students without overwhelming the entire program or impinging on the core content of chemical engineering. After all, we said that only a few are going to specialize, while a large number will require some PSE skills. And of course, while we're teaching this, we're going to be reinforcing the core content. So let's take a look at what that looks like. So I'm not going to show every course in chemical curriculum, thermodynamics and heat transfer and so forth. I'm going to just show the PSE related courses. So here's the yellow are the required courses. So there's a modeling and numerical methods course in 2nd year, a basic statistics course that covers things like regression, design of experiments, a little bit of analysis of variance, and gets into some principal component analysis. So it includes some multivariate statistics in this basic course. We have a flow sheeting course, an undergraduate process control course, which we all love and think is the most important course in the program. And we have another design course here, economics and process operability. And I'll talk about a little bit more in a second. Now, there's a couple more required courses that have options. So in this program, the design course, there'll be several design courses, and one may have a biochemistry emphasis, and another might have a polymer processing emphasis. There's going to be one design course, the project design course, that has a PSE emphasis. So we're going to have 3 design courses, basically. Flow sheeting with some sustainability, the project course, and then another course in the middle. Now, some of you may say, well, gee, how did you do that? And by the way, this is basically the Master Engineering program. How did you get this extra course? Well, most programs, there's a course called Engineering Economics, and it's usually a very weak course. It doesn't have a lot of content. So what we decided to do was to teach the engineering economics in about 5 weeks or 6 weeks, and that gives us a lot of time then to do some novel education and operability and process design, talking about things like in dynamics and operating windows and flexibility and some of the topics that I'm going to discuss, because they're very closely related to Industry 4.0. Then we have some technical electives. So this is and allows us to offer these courses, and they not all the students will take them. There are going to be some students who are in love with biochemistry or nanotechnology, and God bless them, and they don't have to take these courses. There's going to be an advanced process control course, a data science course, and an optimization course. Now, just to give you an idea, these courses average about 50% of the students take them as electives. So that out of our class of 80 graduating, we'll have about 40 students on average in these 3 courses. So this gives us the ability to offer some really good advanced content in engineering to a substantial number of students who are very interested in it. And one of the ways we sell this to students is to say, do you know exactly what you want to do? And then some will say, yes, I want to cure cancer, or I want to build an artificial lung or something. Good. Most don't. So I say, okay, if you don't know exactly what industry you're going into, or whether you're going to emphasize management or operations or whatever, these are the systems topics are the ones that are going to be the most general value to you. So we have, we could just block this out, we have a group in model-based decision-making, a group in process control, and a group in data sciences. Now, these are not hard separations, and we don't have to make them, because there's going to be some empirical modeling that goes on up here, and there's going to be decisions down here, statistical process control, certainly in decision science. But just to give us an idea of how to break it up. So let's look at what's in these courses and what's in the courses now and how we can teach them so that when students are involved with Industry 4.0, they'll know the principles that are important for engineering that carry over to the Industry 4.0 issues. This is a schematic of today's computer digital instrumentation and computer control. So it has some microprocessors, it has some operators consoles, and other special purpose computing. What's good about it? It's decentralized, it's modular, it's scalable. So we can start off with 2 process controllers, add 3, 4, 5 later on. Things that we wanted in Industry 4.0. It has redundancy. So even though it isn't shown here, each microprocessor here is redundant. So there are two processors with a watchdog timer on them. There's limited fault effects. So if this particular controller fails, we only lose control of a few valves and a few sensors, not the entire plant. It's independent of the data communication. So if this data highway goes down, the control is not lost. And that's an important aspect. The operators could then physically move over to where the microprocessors are and still operate the plant for a short period of time. We have an independent layer of protection. So we know that in our safety control for safety hierarchy, every layer has to be independent. If we did the safety in the same computer where we did the control, we wouldn't have this independent safety layer. And we have the options for unique software and intensive calculations that are independent from the control computers. There's some deficiencies. We're still wired. So we're still running miles and miles of wires. We can't do that with Industry 4.0. And we have very poor interoperability. If this is a Siemens system, for example, and you wanted to add one Yokogawa controller to it, the cost would be prohibitive. So once you buy one of these systems, you're going to be pretty well stuck with one vendor. And with Industry 4.0, we don't want that to happen. So while we introduce this, we can show all of the aspects of it that are important. The ones that are good and we want to retain in the future, and the ones that we want to improve upon. Let's look at a little more detail. Now, this is the first sketch here I'm going to talk about is a cyber physical separation system. So this is the way we did it from probably the 1960s until even today. Some systems have this kind of a structure, and certainly most of the installed base that your students will see has this structure. So we have to talk about it. That installed base is going to be there for 30 years. And so we have a digital computer, but then we have what we could say a dumb sensor and a dumb valve. So what we have is only one variable that's being transferred in one direction from the sensor to the controller, the cyber system, if you will. And one variable, the command to the valve, being sent from the cyber system to the equipment. Interoperability here is very easy. 4 to 20 milliamps is the standard around the world, or if it was for pneumatic, even older, 3 to 15 PSI. But we don't have really much knowledge about what's going on in the sensor. Is it functioning properly? Is the valve functioning properly? So we lose a lot with this kind of structure, but that's the structure that most of your students will see if they go out into the plant today. So let's look at a cyber physical system. So with smart devices, now this technology is certainly available and has been for probably over a decade, and it is used in industry a lot, but probably still penetration, given the slow turnover of process plants because they're so capital intensive. The penetration isn't enormous. Here we have a microprocessor at the sensor and a microprocessor at the valve. So now we can have, and there are there's the various ways that this can be implemented, the hard versus other methods. So I'm not going to get into the details of that. But once we have two-way communication, we can make calculations at the sensor. We can do linearizations. We can correct for changing process conditions, have multiple sensors to calculate a variable. And to the controller, we not only give the measured value, but we can give a diagnostic. Is the power supply working in the sensor? Is the power dropping off so that value might not be reliable. We can, from the controller, we can send information back to the sensor. So we can calibrate the sensor. We can set the zero and the span and so forth. And just having been able to do this information rather than having people go out to 1,000 or 2,000 sensors and calibrate each one individually can save millions of dollars, certainly hundreds of thousands. Now we have two-way communication. At the valve, we can do flow stem position linearization or other calculations. To the valve, we can send a command, and also we can send a valve configuration like the data for the linearization or limits. And coming back, we can get diagnostics. Did the valve actually move? If we sent a command to go be at 50%, is the valve at 49 or is it at 38 or 22? So we can get basically the valve feedback position and other diagnostics on the air supply to the valve and so forth. So this is a much superior system. Obviously, standards are now required so that I can buy any sensor or any valve and plug it into any control system from any vendor. So this has taken a decade of negotiations to come up with a standard. Note that we're still hardwired. We're stuck with those wires right now. And that's an enormous expense and an enormous limitation. But again, once the students understand today's system, they can understand the capabilities and the shortcomings. Now, from the process control system, what about the horizontal integration? When I teach level control, once you understand how to control level, you can put levels in series. Now, these could be distillation towers or other pieces of equipment, each one having an inventory that's being controlled. And so now we can introduce things like the feed push system. So in some plants, we're pushing the feed in and it comes out whenever it wants. Now, this has some limitations. So in North America, we have a feed push system to distribute vaccines for COVID. And it's not a good system. Once we push some material to a bunch of hospitals, and then over here, sometimes we have too little vaccine and sometimes we have too much vaccine. Now, of course, we're dealing with a command economy that's trying to satisfy each of the individual political localities, but it's not the best control system. So another kind of control system would be a pull system where we set the flow rate, the production rate here directly, and then we pull material in until we ultimately pull raw materials in. So now we have these two. We have a feed push and a product pull, and once we do that, we can talk about where we need these. So in a chemical plant, the steam system's a product pull. You might have 50 different heat exchangers demanding steam, and they're all doing it in an uncoordinated manner. And once they demand steam, they take it out of the low pressure header, for example. The low pressure header tells the medium pressure header it needs more steam. That tells the high pressure header it needs more steam, and ultimately the boilers have to make more steam. So there are pull systems and push systems in our plants. If you know the first thing about horizontal integration is you're going to have to decide what kind of systems you have for production control in your plants. So we can do this in process control and set up higher level thinking. If there's a constraint, we can put a flow controller in the middle of the plant and have pull systems and push systems in the same sequence. So taking our level control lesson and just going a little bit further, we can get into the horizontal integration. I'm going to skip over this one a little bit, just to say I don't teach supply chain in a process control course, but once they can understand process control, they can see that if you have an unstable system, open loop unstable system with lots of dead times, it's going to be a big problem. Now, vertical integration, we talk about cascades. So we have a temporal decomposition, the slowest, the next slowest, and then the fastest over here. And we take advantage of that temporal decomposition. And I just want to point out that that kind of temporal decomposition can be implemented in the MPC technology. It doesn't have to be individual loops. So you can have individual models for all these variables and have an integrated MPC controller that implements cascade control. I think Shell SMOC controller was the first to do that, but I think others are doing that now. So that once we start looking at the temporal decomposition from process equipment up through scheduling, for example, they will understand the importance of solving fast problems and preventing disturbances from getting into the slower responding systems. But this remains an active area of research to integrate these systems. I don't want to imply that temporal decomposition is a solved problem, even though theoretically you could have the biggest nonlinear MPC in the world. In practice, it's not going to work. Now, what about if we can't measure what we want to control, or that the sensor is too costly? So here's a little flash system. So we have a couple of heat exchangers, a lower pressure in the flash vessel. The liquid comes out the bottom, the vapor comes out the top. Most students calculate flash calculations in the thermodynamics course. They never see a picture like this to say, well, what would it look like? What does the equipment look like? And I'm afraid our thermodynamics instructors are never going to do that, so it's going to be up to us to do that. And let's say we have this feed, some light hydrocarbons, and we'd like to control the light key as the ethane, but it's very expensive to put an on-stream analyzer with the analyzer house and the sample system. It could run $30,000, $40,000 capital easily. So let's look for something that's related. Now, we can't do multivariate statistics in the process control course, but we can use our basic chemical engineering knowledge, although we're going to do the multivariate statistics in a little while. So we could use our chemical engineering knowledge and recognize that there's a relationship between the temperature in the flash and the ethane in the liquid. And we can analyze that for base case and for disturbance cases with different feed compositions. And while we know that isn't perfect, if that's going to control ethane within the acceptable limits, we can control the temperature rather than by the analyzer. And in many cases, in practice, we do that. So once we've taught inferential control, the next step is to say, well, what if it's not obvious? What if from physical principles we can't find one or two sensors? What do we do? That's the next course. That's data sciences, and that sets them up for Industry 4.0. And of course, if you get to the point where in the second course you can do centralized model predictive control, then we can look at the value of integrating the horizontal or the vertical optimization decisions to get a better overall dynamic performance. So those are some ways that we can modify slightly our teaching and make sure that we build the links to the ideas that are important for Industry 4.0. Now, what about process design, the process design course? This is an alkylation plant. Don't bother with the details. We have two feeds coming in, a C4 and a mixed olefin stream, and we're going to make an alkylate, and we're going to blend the alkylate then with other components and make some gasoline. It's not very straightforward process. And if we had time, we could talk about it and talk about the control and everything. But let's just talk about one thing, operating window. When we're talking about the horizontal integration of a plant, we have to know that what is the plant, the capacity for each unit, and then what is the plant for the capacity for the integrated plant. So let me just go back. So we're going to look at just some flexibility. We're going to change the production rate and the octane of the gasoline because we have different octanes that we're going to sell. And this is the operating window for that plant. The reds are infeasible, the blues are feasible. So this is the blended flow rate in barrels per day, or barrels per batch, and this is the minimum octane, which is basically what we're going to run at with an optimized blend. Here's the design point. We're right on the edge. We have no flexibility in this direction at all. So this is a design that probably would not be acceptable to people. So we'd have to go back in and look at why we can't increase our production rate or increase our octane a little bit and still be able to run a feasible plant. So teaching the operating windows is very, very important. If you want to know the horizontal integration of a process, you have to know the operating window. Now, just because the operation is feasible does not mean it's a good idea. So there's something called the integrity operating window. And so the green area is safe operation, good operation. And we want to keep our targets within that. Then outside that, we're going to damage the equipment. We're going to damage it slowly. Failure occurs with sustained operation in this region. And of course, if we go further out, this could be pressures or temperatures or whatever, failure occurs very, very quickly. So out here, we could have loss of containment, the vessel would break. Now, if we have some operating data, we have the data that looks like this. Now we see that we've gone outside the green zone, and we have to, every time we go outside the green, we're going to accumulate some damage. And the more damage we accumulate, the sooner that the equipment will fail. So the integrity operating window is smaller than the operating window. So let's look at an example. Here we have the head curve, the head versus flow. So this is a normal head curve for a centrifugal pump, constant speed. We teach these to our students all the time. And we have the best efficiency point. So we tell the students you should run at the best efficiency point. And we tell, and all the engineers know that. The problem is a lot of engineers run the pumps at low flow rates. Well, it's still on the curve. So what's the problem? Well, the problem is this is the reliability curve. And as you get away from the best efficiency point, you're going to have very, very low reliability. So you're going to have low flow cavitation. You're going to damage the impeller so that rather than running 5 or 6 years, this pump over here is going to run 1 year and then it's going to break. You're going to damage the pump. So there's an old statement, pumps don't die, engineers kill them. And engineers kill them because they don't understand how a pump works. They've been shown this curve, and that's all they know. So when we're teaching design, we want to make sure that we teach reliability. So in this particular case, if the plant is going to operate at low flows for any sustained period of time, we're going to have to build a control system to prevent the low flows going through the pump. And we can do that simply by adding a recycle. And that's very, very commonly done. Now, if we're going down here for 5 seconds and come back again, that's not going to be an issue. But if we're going to be here for sustained time, we're going to have to add some control systems to prevent that from occurring. So, and when we're teaching design, we teach reliability. we start building what's needed for I 4.0. Now, as far as maintenance is concerned, this is a little decision tree that was adapted from NASA. And down here are final decisions. And let's just talk about the final decisions. If you have extra time later on when you're viewing this, you can stop it and read all the decisions. We can run to failure. Now, we do that with light bulbs in our home, and that's no problem. If the light bulb fails, it's no main problem. That's not good for most process equipment, but perhaps for some it is. Then we have design to prevent damage so that we extend the life of the equipment. And that's simply like the pump that we just talked about, having a recycle around the pump. Now we have preventive maintenance, interval-based. If we have for example, in your car, you might change your oil every year or 12 months or 10,000 kilometers, or whatever it happens to be. Spark plugs, 100,000 kilometers. What if you've got 100 pumps in your plant from different manufacturers, different sizes? How do you manage that whole system? You need the industrial Internet of Things. So you have to know how much time each machine has been in service, when it was maintained, which parts were replaced, etc., for all your 100 pumps. In addition, you have to know that for all your valves and all your compressors and all your sensors. Obviously, that's not something that you want to do with 3x5 cards. So there's an opportunity for the Internet of Things to improve the preventive maintenance. Now, what about predictive maintenance? So now we have equipment. We don't want to do this on interval-based. Something may go wrong at any particular time, and we'd like to know if it's an incipient failure. It's going to fail in the future, but we'd like to know that so that we can schedule maintenance. We can do the maintenance before any damage occurs or any lost production occurs. So we can make a smart pump. We can measure all these things in the pump, put a processor on it, have it communicating in real time with the Internet of Things system, the Industry 4.0. So the cyber physical systems for monitoring and diagnosis, obviously very, very important. We can introduce these for some obvious ones. Later on, we're going to talk about the data sciences approach to this. And finally, the process, I think this is one final one, the cyber physical systems. Most equipment can be enhanced with measurements and computation. This is a chiller in the McMaster boiler house. We're really cold here in Canada, so we have boilers, and occasionally it gets warm for about a month and a half in the summer, so we need air conditioning. So we have these industrial chillers, and we send the cold water to all the buildings from a centralized control room. So we use this as a chemical engineering laboratory, depending on the instructors. When I was teaching some of the design courses, the students would come in here and learn about equipment because it's industrial scale, and you can go and walk around and touch it. So this chiller is just cooling water for air conditioning. But modern chillers are provided with embedded controllers. So what we want to tell our students is there are business opportunities. Whatever you're building and whatever you're doing, there's a business opportunity for making it smart and beating the competition. Okay, so another topic in design that we teach is troubleshooting. So I can remember when I first went into industry and I looked at some drawings and I said, my God, why are we measuring all these things? So I would go and find somebody who was older than me and knew, and I'd say, why are you measuring this? Why are you measuring that? And then pretty soon they got tired of me, wouldn't talk to me for a while. But we need those so that we can monitor the health of the system. So we measure delta pressure across the trays so that we can't look inside, but we can infer the hydraulics, the liquid and vapor flows in the tower. And we do that in different sections of the tower. We're measuring a pressure here, even though there's a pressure controller here, because we want redundancy. Pressure is the key variable, so we want redundant measurements. We can compare them. A tray temperature. This isn't a heat exchanger, so why are we measuring temperatures in the middle of the plant? Well, of course, there are inferences of if it's boiling hydrocarbon or boiling multi-component system, that's going to give us an inference of the composition in the tower. And we can measure the liquid level in the condenser. And why would we do that? Well, this is a flooded condenser, so we cover part of the heat exchanger with liquid, and that changes the heat transfer duty. So if we want to condense more material, we'll reduce the liquid in the condenser. That'll give us more area for condensing. If we want to condense less, we close this valve a little bit and fill it up a little bit so we have less area. So we need all of these sensors to monitor the health of the process. Once we understand those basics, then what if there's a fault that isn't obviously sensed by one or two sensors? Well, that sets the students up for the advanced technology in Industry 4.0. I'm going to spend just a couple of minutes on this troubleshooting because I think it's an important aspect of education that is not given enough attention. The University of Michigan, Fogler teaches this, and we've spent a lot of time at Master developing the teaching approaches. So if we have a current state and we think there may be a problem and it's not time critical, we're going to do our troubleshooting, we're going to fix it, and we're going to return to operation. If it's time critical and it's only moderately time critical, we're going to go to a safe park situation. And there's been a lot of research done on what a safe park is, but you could think of it as reducing temperatures, reducing production rates so that the equipment is in a more stable operation. Go ahead and troubleshoot, fix the problem, return to normal operation and go. Or if it's highly time critical, we're going to have to shut the plant down. There's something really wrong. The pipe is broken. We think there's some material, some fuel that's being released. We got to shut it down immediately. Then we troubleshoot. Then we fix the problem, and then we have to start the plant up again before we return to normal operation. And then the troubleshooting follows one of any number of different troubleshooting approaches. We use the 6-step Don Woods approach, but there are other ones around, but this one certainly works very well for us. And for example, we have a number of maybe 30 or 40 cases that we use in teaching. So this is just a little example, one of the simpler ones I'll run through very quickly. This is a physical system. We have some liquid in a tank where we have 2 pumps. We have a spare pump, of course, because if we need reliability, we need a backup. And one of them will be in operation at a time. And then we have a flow control that adjusts the valve here. And we have pumps A and B. And so we would tell the students, they work in groups on these problems. Pump B is working very well. And we can see the flow is at its set point, and the controller output is in its range between 0 and 100. So that's what's being sent out by the controller. And we're very happy. Everything's working great. Now we come along and we say, the maintenance engineer says, I want to turn B off and run A for a while so we sort of balance the amount of time in operation for both pumps A and B. We don't want to run B all the time until it fails. We turn on pump A and turn off pump B, and things don't look good. The controller output goes all the way up to 100%. It's a fail-closed valve. That means it's fully open. And the flow isn't getting up to the set point. And then we ask the students to troubleshoot this problem. And they can ask questions, and they'll be given answers, succinct answers to reasonable questions. So they might ask, is the liquid here down too low and we're sucking air or vapor into the line? And then we'd say, okay, well, we just looked at the level sensor, and the level is at 70%, and the takeoff is down to 5%. Then they might ask, well, what about some of the valves here? So maybe these valves maybe somebody forgot to open one of these valves. And we come along and say, no, all the valves are open. And then ultimately, through the troubleshooting, they would conclude that the operators left these two valves open, the isolation valves open, and the one-way valve here has failed, and it's failed open. So what we have here is a circulation. So a lot of the liquid, rather than going out in this direction, is circulating around and around. We're losing head in the pump, and we can't pump as much material as we want. So these are the kinds of things that happen in troubleshooting. So we'll move on to optimization very quickly. The optimization course looks at a wide range of models and solution methods, LP, MILP, NLP. It emphasizes converting the problem statements into solutions. We make use of available software tools like Excel, MATLAB, and GAMS, and really emphasize explaining solutions in engineering terms, sensitivity analysis, and so forth. And the students, once we get to projects, the students are allowed to define their own projects, and they love that. So what's the first problem that almost everybody does? Even mathematicians do this. They do the gasoline blending problem. That could be because Exxon Corporation, way back in the 50s, when they were known as Standard Oil, they published a book on linear programming before most engineering faculty knew anything about it. And one of the problems was the gasoline blending problem. Has become famous, I guess. It's an interesting problem in its own right, and certainly important for chemical engineers. So that's nice for us, bad for the mathematicians. So the first thing we do is we give them a simulator of the system. And we say, okay, I want you to make 7,000 barrels of gasoline meeting these specifications and maximize profit. It sounds like a pretty easy problem. There are specifications, maximum and minimum, octane, RVP, and volatility. And with a simulator, you think you could do pretty well. We give them a half an hour, and most of them will find a feasible solution. Almost nobody finds the optimal solution. What's the lesson? Once you have a simulator, you should want an optimizer, because if you don't want to run thousands and thousands of cases to find a good solution. So optimization is essential for the full benefit of the models that we all have. Now, that's an important lesson for them. We want to be able to explain their solutions and look at sensitivity. So for that blending problem, if we change the production rate from the base case below, down, and up, we go down to a certain point, the system becomes infeasible. And up to over almost probably 8,000, it is feasible. So even a simple unit can be a challenging problem. And here's, again, a horizontal integration problem. This was a very, very simplified petroleum refinery. This is a project that the students would solve in about 3 weeks' time. This is a crude distillation unit, a reformer, and a catalytic cracking unit. So it's a very, very, very simplified problem. They have various feeds that they can buy, and they have different operating conditions. And this was set up as a linear programming problem. And so this is the kind of problem that enables them to think about operating several units in sequence in an integrated manner, we see that some of the materials can either go into a product or into a reactor and then to products. Really important for them. If they're going to deal with Industry 4.0, they need to understand operating decisions. Now, data science, luckily with data science, the advanced course does regression, principal component analysis and partial least squares, cluster analysis and neural networks. So a very advanced course really for an undergraduate level engineering. Again, emphasizing converting problems into solutions. Available software is Excel, MATLAB, ProMV, which is a product, it's a spin-off product from McMaster. It's a commercial product, and it's also the basis, I think, for some of the work that's done by Aspen Technology. Again, emphasizing the solution, explaining the solutions, and again, allow students to define their own projects, which is very critical for the satisfaction of the students. So we need to build a model that suits the application. So we need causal models for optimization and for process control. And so here we need to be able to have a cause-effect relationship. When I change this valve of the fuel, I need to know the effect on temperature out of the heater. When I change the flow of normal butane, I need to know that effect on the octane, the vapor pressure, percent volatility, and so forth. These have to be causal models. So when you're building database models, in some cases, they're going to be causal. In others, they're correlation-based models, sometimes called prediction models. So on an inferential soft sensor, when we're going to build soft sensors, when we do process diagnostics, we need correlation-based models. And the distinction here is really critical, and it's for some reason it takes a while to get people to understand. I have seen industrial cases where people have built correlation-based models and then tried to use them in optimizers and found, gee, the results were going in the wrong direction. We're not optimizing the plant. So with the causal models, we're going to have to perturb the process. We need to experimental design is a key for success, and we want to do this. When we do this experiment, we want to reduce disturbances. So if the plant is changing production rate or changing from one feed to another, you're not going to run your experiment then. Because we want a simple cause-effect relationship between isolated variables. Correlation-based models, we want normal operating data with typical disturbances. So statisticians would just call disturbances variability. It's just variability. No experiments. And we have to take the data under the conditions in which it's going to be used in the future. So if there are control systems and actions by personnel, we can't avoid those. We can't turn off the controllers. They all have to be in there when we're building these models. So reduced-based models are really kind of, the concept is very easy if you're talking about a process to an engineer. So if we had 1,000 sensors here, how many directions, how many independent things can happen? Well, we know that the feed flow rate can change, the feed composition can change, maybe the cooling water temperature can change. This is really a low-dimensional system. Only a few things can change. And if we went from 40 sensors to 100 sensors, the complexity of the plant is not changing. So we know that we should be able to represent this with a few variables, but not a few measurements, a few latent variables. So in the data I'm going to show you, there were about 40 measurements on this distillation tower. Now I can't draw in 40 dimensions, so I'm going to draw in 3 dimensions and show that here's some data that are in 3 dimensions, but or 3 variables, but the data really falls in a plane of 2 dimensions. So even though there are 3 measurements, the data is highly correlated. Now, in reality, the data from these 40 measurements would go down to, I think, about 3 latent variables. So using multivariate statistics, we can determine the latent variables and look at our operation in that latent variable space. And then we can build an inferential model that uses all the measurements to find the latent variables and then relate the compositions to the latent variables, and then ultimately to all of the measurements with different weightings. And does that work? Sure. This is if we didn't have any inferential control. This is the percent benzene in the feed, so that's a common disturbance. And this is the deviation from 0 between the actual and the predicted product quality. So this would be perfect. That black line is perfect. If there were no inferential control, we'd have big deviations. If we use 1 temperature, we would get this line, and the red line, much, much better, is using multiple temperatures, using the multivariate statistical model. Oop. Okay. So, kind of in summary, what are we doing reasonably well? Math modeling and simulation, especially flow sheeting. Introduction to advanced methods and tools, and in all of the, especially if you have these courses in place, process control, optimization, data sciences. Open-ended projects and advanced courses. We're doing all of these things reasonably well. What can we do better? The complexity of the plant-wide operation and control, vertical and horizontal integration. To a great extent, our design courses do flow sheeting and cost estimation, but they don't talk about how these things operate. We need to think about how they operate so that we can take advantage of the tools and the vertical, especially the vertical integration in I 4.0. Increase coverage of equipment and instrumentation, and especially their faults. If we want students to understand that fault diagnostics are important, we have to teach them that equipment fails. And we don't do that very well right now. We want to introduce reliability as a topic in the course, in the design course, or somewhere else in the program, and troubleshooting. And we want to emphasize the importance of safety and security. So what steps can we take? So, and offer advanced elective courses on control, optimization, and data sciences. Increase the coverage of operability in the design courses. More content on equipment and faults. Now, quite often instructors say, well, I don't know this material. Well, we could get some guest instructors to help in that regard. And then become aware of the initiatives in Industry 4.0 and then build explicit links in the courses. So when you talk about the certain, we started off with, here's the current digital control system with smart valves and smart sensors. It has lots of good capabilities. It has some limitations. It still has wires. If you teach that, and even if you just teach it and you don't even say, well, in the future, there's going to be something called Industry 4.0. They're going to be capable of making that jump. So that's my wrap up. I'd be happy to hear your questions, your comments, your opinions, objections, whatever we might want to talk about. This is my email, and this is the link to the process control website that also has some of that operability and designing material in it. So could we move to questions now?
Yes, Professor Malin. So thank you very much for your comprehensive and insightful presentation. It was enlightenment, I believe, for all of us. So yes, I think we can open for the Q&A session. Anyone who like to give opinion, comment, feel free to maybe raise your hand. You can talk orally, otherwise you can drop your inquiry in the chat box.
Dr. Agus, I think we have one in the chat room during
Sure.
Prof. Marlin giving his talk. The question is from Dr. Samsul from USM. I will read from what he put in the chat. Prof. Marlin, in your point of view, do we need to revamp chemical engineering curriculum to embed as much as possible of IR 4.0 related courses? Issue is how much to add and how much can we leverage on the conventional chemical engineering course?
Well, I think first of all, I think it would be premature to try to now change the curriculum to match Industry 4.0 because it isn't clear what Industry 4.0 is. It's a developing concept. So I would say that what we should be doing is sort of what I said here is that around the edges, if we teach optimization well and data science as well and process control well and design well, and we expand, I think in a meaningful way, not really even worrying about Industry 4.0, but preparing them for their future careers. Rather than say teaching it in a limited way, so let me do some caricatures of a limited way, would be a lot of frequency response in the control system, in the control course, or a lot of flow sheeting and economics and nothing about how the plant operates in the design course. Or an optimization course that concentrated more on the Newton step and line search methods and had students do a lot of programming in that rather than solving realistic engineering problems. So I don't think we need to restructure. The plan that I'm presenting here talks about a rather substantial number of courses in the systems area. In the core courses as well as the technical electives. And I think we want to be sensitive to the fact that while we think, when we look in the mirror, we think that we're the most beautiful people in the world because we're systems engineers, that there are biochemistry students and nanotechnology students and environmental engineering students and a broad array of other topics that aren't that interested in concentrating in process systems engineering, and we want to keep them, I think, all in the chemical engineering program. And so what we want to do is reduce the number of core courses and allow streams to go off into bioengineering and environmental engineering, and then have a very strong stream in process systems engineering. So that's the way I look at it now. I don't think we have to completely retool the program.
Professor Marlin, we have the second question here from Dr. Faisan Ahmed. I think it's from Pakistan. His question say that the world is changing, revolutioning, and we have to keep pace with it. So he asks whether shouldn't we go to more practical knowledge for process control than studying things that we know that no application in the modern in the industrial world. What would be your opinion on that?
Well, I think certainly the control technology. There's a broad range of control technology, and for example, I don't teach everything in my textbook. And you might say, well, why is it in the textbook if you don't teach it? When I did a market survey, every professor said, you can put anything in your textbook that's new as long as you put everything, you include everything that's ever been in a textbook. And that's why these textbooks are getting bigger and bigger and bigger. So, for example, I don't teach frequency response. I do very little or nothing on stability analysis. Other than looking at processes themselves, are they stable or unstable? So the level process is unstable, for example. So I would, so I think that there's a lot of residual, vestigial material and process control books and courses that can be taken out and still make it an effective course. I would not, some people, I think at the most extreme would say, let's stop teaching PID control and let's not teach cascades and feed-forward. We can do everything with mild predictive control. But I think that's not realistic. There are lots and lots of small plants, water treating plants, sewage treatment plants, plants of all kinds that have only need multiple single loop control. And even more sophisticated plants, for example, a company asked me to teach some courses at their ethanol plants. So they make ethanol from corn to add to gasoline. Each of those plants only has about 3 or 4 engineers, and they have nobody that knows anything about control. And my task was to go in and give them a little bit of control so they could keep their plants operating. So lots of people who need elementary control. And so we certainly want to teach the basics of step testing, tuning PID controllers, loop pairing, and adding control to basic process units like fired heaters and so forth. Now, I'm not sure, I hope I've addressed the question, but if I haven't, because if you have some specific suggestions about how the course could be taught, I'd be happy to hear it. Now, I mentioned that in our advanced digital control course, we do a lot on model identification, we do model predictive control, but that's for the half of the students who are really interested in control. And we're getting half of the students who are taking a relatively advanced program.
Thank you, Professor Malin. Dr. Farzan Ahmad, any further comment? Okay, we have new questions from Dr. Ramasamy from University Technology Petronas. He said that thanks, Professor Malin, for the thoughtful lectures. What is your take if we teach everything in the time domain, avoiding the Laplace domain completely, and we include more on the different control strategies? What?
Yeah, that's I teach almost no frequency response. I still do a little bit in Laplace transform, so that for 2 reasons. One, so that we can talk about what happens if you put two first order series systems in series and 3 and 4 and 5 in series and so forth. And what happens to the stability and to the damping and so forth, and you can get that directly from the models in the Laplace transform domain. But that's my personal take. I think you could teach, and I spend very little time on that. I think it's more important that they understand it in the time domain. And a long time ago, I tried to teach the frequency response, and students could pass the exam perfectly. And then I taught them in the design course, and they didn't understand a thing. Nothing carried over. So the more time domain, the better, as long as we get them ultimately to understand causality and things like the effective dynamics on control performance, how to pair loops, and really put some control on some practical units. So even though I stay in a little bit in Laplace transforms, not in frequency response, I would have no objection if somebody said no Laplace transforms at all. I think it's a style issue.
Hello, it's Moses Tardy here from Perth. Hi, Thomas. How are you doing?
Very good. Nice to meet you.
Yeah, nice meeting you. Excellent work, and I met you many moons ago now. My question is probably a little bit open-ended, so you need to decide how you want to take it. Having been in management for many years, and now back to later part of my life, trying to do a bit more teaching and come back to teaching this unit. It's quite interesting to see that I suppose as far as teaching and delivery and students are concerned, I don't really think much has moved in about 15, 20 years. That's one comment. But I'm particularly keen on how, with the pandemic, how have you adapted the content of your teaching with regards to the labs and experiments, and also the assessments and project really for this particular equivalent unit for your campus? Is there anything you can share with us in those areas, please?
Okay. I had not taught during COVID. I was scheduled to teach a master's level course, and it was canceled because there were no students. So, but I can say a couple things about the laboratories and process control. I was teaching in California for a number of years now, as well as McMaster. And a colleague there was teaching a process control course during COVID. And rather than have them do the labs in the laboratory, he purchased some of these small heat transfer labs that were developed by Hendricken at, I think, Brigham Young University. And they're available for sale, and you plug them into your PC, and they interface with MATLAB, and you could do identification and single loop control and multi-loop control and feed forward and things like that. So each student got one of those individually, and so they didn't have to come to the university. So that was a very good thing. For the other labs, he had to go into the labs himself and do a lot of video, and then just give them data sets, which is not a very good system. As far as the comment about things haven't changed much in teaching, I'm afraid that's true, but it shouldn't have. Over the last decade or so, I've been learning from the cognitive psychologists, and there's a lot of research done on teaching and what's really effective. And rather than talking to some old teachers and saying, well, how do you do it with no evidence, these psychologists are doing very controlled experiments on all kinds of aspects of education. There's a website called the Learning Scientists. And if you Google the Learning Scientists, they have some nice material, and there's a book that you can download that has a very good summary of a lot of the developments in education developed over the last maybe 20 years. And then they have some other good summaries, and there's some nice people there. My personal, I have switched mostly from lecturing to doing the flipped class approach when there are human beings in the room. And I really like that. That works very well. It puts some emphasis on the students preparing before class. And so for the process control course on the website, there's a whole bunch of workshops that are really intended to be used as the flipped class where the students do the e-lessons before class and we do workshops during class. And the solutions to those workshops are available to academic instructors. So you asked an open-ended question and I went all over the place with my answer. Sorry.
Thank you very much.
Okay, nice to meet you.
Okay, thank you, Professor Malin and Professor Moses from Australia. Dr. Hendra from South Korea, do you like to ask any questions?
Yes. Can you hear me?
Hello.
Hello. Okay. Thank you, Professor Marlin, for a very interesting presentation from you. I learned a lot from what you have just presented. Although I'm not a chemical engineer, I'm basically doing control engineering for electrical engineering and a little bit in aerospace engineering. But my impression is that I have one comment and one question. The first one is my comment. From what I observed, the fact that control courses actually, in my point of view, is very limited for undergraduate engineering in many places. So, and then it seems that we do not benefit much from the advancement in the development from automatic control and system engineering community. So I'm afraid that we kind of losing a common language among engineering fields, because when you come into the reality and working in the company, and I believe chemical engineers are not talking with only chemical engineers, but also with people, say, for example, electrical engineering, for example. So what, in your point of view, how can we bridge the gap so that we at least can understand more each other in terms of language, control language? That's the first thing. The second one is learning from the fact that this in the current development in control theory and maybe applications, we are facing industry 4.0 is the capability of learning. What I mean by learning is that we have a very complex, I believe chemical processes are very complicated, and then with a high complexity system and large scale and involve I don't know, a lot of variables to measure and to analyze. So I think to build a very reliable model is very expensive and perhaps a time consuming. What do you think that about benefit from learning, say, for example, artificial intelligence and incorporated in the process control? I think that's my questions. Thank you.
Okay, let me start with the learning first. I think there certainly is opportunity there. And probably there should be learning that's bounded by physics and chemistry. So that so when you're building, let's say, a neural net model, the result shouldn't say that if I put 5 pounds in, I can get 6 pounds out. So we should be able to learn from the data, and also observe the first law and second law of thermodynamics, material balances, stoichiometry of component balances, and so forth. So I think there's a lot of opportunity in looking at some of the more complex biochemical and chemical systems and learning control. I mean, it's been used commercially even on things like batch-to-batch control, where we iteratively learn. But there's probably hasn't been a lot of industrial application of that. I think the data sciences have been extremely successful in inferential control, building either least neural net or partial least square models for inferential control has been a huge success. So that's surrogate values, using surrogate variables, calculated variables. It's had some limited success. at fault diagnostics and incipient fault identification. That's and some of the people at Master, not myself, have published some very nice results on that, for example, in steel making, in real industrial applications. And that was 15, 20 years ago even. But I think there's still a lot in learning that could be done. As far as the control language is concerned, I think the chance that we're going to educate undergraduate chemical engineers to talk in singular value decompositions and so forth, it's going to be rather difficult. I think that's going to be at the master's and the doctor's level. So I think there's the master's level, sort of a course-based master's with a project. So kind of a short master's, 1 year, concentrated in systems engineering. There you're going to be mixing mechanical, electrical, and chemical engineers. Those are not going to be chemical engineering courses. They're going to be systems engineering courses. And that's where the people are going to learn the terminology so that they can communicate effectively. And of course, the PhDs who've done, spend 4 or 5 years in research. So I don't think that we're going to get the control engineering community, the undergraduate chemical engineers, to the point where they're going to be able to talk to somebody who's taken a course in communications and some mechanics of the vibrations and mechanics of machinery and so forth, and the mechatronics of the system. But at the master's level, even once you start mixing them and putting them in courses, and that's what we're doing here for what we call a professional master's, it's not focused on research, and we put mechanicals, electricals, chemicals together, then I think they can communicate. But undergraduates, other than, of course, they're going to learn on their own, and some will be able to do it on their own. But the preparation in the undergraduate program, I think, is more than we can do.
Okay, thank you very much.
Okay, good to meet you.
Okay, thank you, Professor Malin and Dr. Hendra. We have another question from Dr. Rizka from University of Indonesia. He commented that your textbook has been used for decades to teach process control. Even I use it to learn when I was an undergraduate student. Related to your talk about the development of science and process control, reliability, and troubleshooting, in your opinion, what would be the most essential to be taught in process control if the curriculum only limiting syllabus based on the textbook?
So I guess if you're talking about what's essential, that would be in a 1 semester course, not allowing a second semester. And what I would like to get to is, and I was probably more able to do this in California, is when I taught the control course, another instructor was teaching a design course, and I could give examples in my course of control issues that existed in the course that the students were studying at the same time in the design course. And I think that's the most essential thing we could get to, is the students are motivated, they have real problems they want to understand, they're real engineering problems, not how to drive a car or something like that, which is a real engineering problem, but it's a little off the tracks for chemical engineering. And as much as you could get to getting them to be able to apply control to some real chemical engineering problems that they're interested in is probably the most essential thing. If I were going to cut anything, so I've taught maybe 50 industrial short courses in control, going to companies. When I do those courses, I never teach fundamental modeling. I start with identification. I start with a little bit on the purpose of control and benefits and so forth, but I don't do fundamental modeling. And those engineers still, they're doing control. The minute they walk out of that room at the end of the course, they're control engineers. They're in the company, they're going to be put to work in control engineering. So I would limit, if I were going to cut the course down, if you said you don't have 15 weeks, you have 7 weeks, I just wouldn't do the dynamic modeling. I would start with identification because you have to get to doing control.
Yeah, thank you, Professor Malin. I think that's answered those questions. The next question was from Mr. Kuntoro. He is asking that your presentation is about preparing the undergraduate for Industry 4.0. What is your advice to junior engineers who just enter the industries on how to embrace with this Industry 4.0?
Yeah, that's well, these first of all, that's a huge topic. If you're not going to have the support system of the faculty members and the teaching assistants and the textbooks and everything, I would have to pare that down and find one topic in here. Maybe it's data sciences. And then I would look at Coursera and other online courses which are probably not quite as demanding as the university courses, but would get you started in the field. And after you've taken that, then maybe you could either talk to somebody in the company or one of your ex-professors to see what additional material there is that's available for you to learn on your own. So it's very commendable that you want to learn on your own, and it's a big challenge in some of these fields. However, if you have the dedication, I've been impressed by what's available online. In teaching design courses, for example, every year you pick up a new process and you've never maybe seen that process before. Then you're the instructor. The first thing you do is go on the internet, and pretty soon you know an awful lot about the process. There's an enormous amount of material. But to get started in a topic, you probably want to look at Coursera or one of the other online, something that you can find on Google. They're pretty good for starting many topics. If you can get your company to send you to short courses, that's also, of course, useful, but sometimes companies want you and not learning.
Thank you, Professor Malin. Mr. Kuntoro, feel free to add any comment if you still have any. The next question is from Dr. Noraini Muhammad from Xiamen University, Malaysia. Thank you, Professor Malin, for the insightful sharing. I have a few questions. Is plan-wide control is a good future for Industry 4.0? Currently, we are not teaching the undergraduate student on plan-wide control. However, it is mostly offered in the advanced courses. Should a lecturer start to teach the plan-wide control to undergraduate students in the control class? And second question is, any comment or opinion from your side on the multi-scale control?
What was that? August?
Multi-scale control, Professor Malin.
Multi-scale. Well, the challenge with teaching plant-wide control, there's a number. First, it's quite complex, but it's the students have to understand a plant, and most students in the control course do not understand a plant. They don't understand any one. You can't say, here's the alkylation plant or whatever. It takes you a long time to build up the fundamental knowledge of that process before you can start talking about the control. So plant-wide control, I think, has to go into the design course. And certainly in California, last 10 years when I was teaching there, the design instructor, Dr. Robert Young, had spent many years in control. So he could teach the plant-wide control in the design course and did. And I think that because in that course, they are flow sheeting, they are looking at the process chemistry and the process economics, and then they understand the problem, and then you can add the control to it. If in control, you just throw them into a plant that has any complexity at all, they're not going to be able to understand the plant, and they're going to struggle with the plant-wide control approaches. So the master's course, I was scheduled to teach this fall and didn't because of COVID and the lack of students. One of the topics in that course was going to be plant-wide control. I'm sorry, I just don't understand multi-scale control. August, could you help me on what the meaning of that is?
Dr. Narani Muhammad, would you like to maybe say anything directly?
Hi, Prof.
Yeah.
Prof. Malin.
Oh, hello.
Okay, thank you. Okay, thank you for the answer for the plant-wide control. Okay, so I understand that it is quite complex to teach for everybody. So for the multi-scale control, what I mean is we separate the control mode into two different modes. Okay, the much simpler mode and the much harder mode, and then we combine together, make it multi-scale control. I think we have a guru of multi-scale control here, Dr. Jabran from Curtin. So do you think it is a good approach to develop a good control by the means of multi-scale?
I'm not familiar with it, I'm sorry. I know there was, at one time, some of the German companies were very keen on, I think they called it eigenvalue control, which we're looking at the eigenvalues of the system, which are really the dynamics of the system. And basing some of the control loops on the eigenvalue control, and basically using the eigenvectors as to define control variables. I don't think that was very successful overall, and that other approaches to, for example, the multivariate analysis to find inferential variables extended to dynamics have been more successful. But as far as multi-scale control, I have to admit my ignorance, and so if I'm really ignorant, I should probably stop talking about multi-scale control.
Okay, thank you. Thank you very much, Prof. Really
Okay.
appreciate your opinion.
Thank you.
Thank you, Dr. Narani and Professor Malin for the response. Any other maybe opinion, comments to Professor Malin? Maybe the last one. Anyone would like to give some final comment, opinions?
Hello.
Oh, yes, please.
This is Khairia from University Technology Malaysia. Professor Malin, hello, how are you? Thank you very much for the very informative and very eye-opening talk. That's really interesting. I'm really interested about you are using flipped classroom and you're giving your students the real world problems to solve so that they can you mentioned a few times that it should be meaningful and making sense of what's physically happening and what is happening in industry when we teach control. You also said that in your more advanced courses that you give your students the choice to choose their own problems. Now, I also use real world problems when I teach control, but and it can be quite tricky because we want the students to be able to solve the problems and see the control behind it and not get stuck on the computing part. So how do you how do you vet through the students' problems to make sure that it's doable within the time frame that we have when we're teaching them? Thank you.
Sure, that's a good question, and it's always a challenge that the students don't completely understand. So we have usually when the way the course would be run is the students break up into small groups of 2 or 3, and then they write a very short proposal, very short, maybe no more than 1 page, and they have to explain their problem, but also give an idea of where they're going to get the information for this, the models that they're going to develop, the chemistry or whatever it happens to be, or get where they're going to get a data set if it's a data science course. And then it's a negotiation process with each individual group. In some cases, and by the way, usually I would give maybe 5 or 10 or 15 sample projects, and they could choose one of those, or they could develop their own. And the majority want to develop their own. But for their own projects, then we have to look at it and say, is it challenging enough? Is it too simple? That's not usually the case. Usually they don't recognize it's much too difficult. So we have to pare the problem down and make sure that they can get the data. In some cases, a very few cases, I have to say you have to come up with a different problem. It's just way too difficult. But if they're solving a problem that has continuous and integer variables, for example, in an optimization, say, well, the minimum you have to do is solve the continuous variable problem. And that would be good enough for your project. And a stretch objective is to add the integer variable solution solver to it. So we give them a base case, sort of a minimum, or let's say a good outcome, and then a stretch outcome that they can work towards. And then for some of the projects in control where you need a dynamic simulator, we try to limit some of the projects down into something that is a linear control system, or there's a nonlinear simulator available that they can use. Because in a course, they're doing this through the course, but if they're only committing the maximum of 2 weeks, if you could say they had a 13-week course and a 2-week project, although they do it during the last 10 weeks of the course, there are still other things going on, which is probably true in your course. So we have this staged approach of a very brief proposal, a more detailed proposal, and then a final project report and an oral presentation, so that we try and corral them into to a feasible problem through those first 2 proposal stages. I hope that responds to your question.
Yes. Thank you very much.
Okay.
Thank you, Dr. Khairia. Thank you, Professor Malin, for the response. Seems like I think we have to stop here. Otherwise, it will continue until the next morning for Professor Malin. It's midnight in Hamilton.
Yes.
Okay. So, okay. Once again, Professor Malin, on behalf of MyPCS and everyone here, thank you very much for your availability.
Well, thank you very
And,
much.
yeah,
I
and
enjoyed
hope-
this.
Sure, and hope that we can have you again in the near future for another topics.
Oh, yes, that would be fine. But
Okay.
not a difficult one. This one was too difficult, August. You tricked me into it.
Sure. So once again, thank you very much on behalf of everyone.